So up until this point, we've talked about reactions as really going one way, reactants forming products. But most reactions have a forward and a reverse reaction taking place, a back and forth. To illustrate this, I have two graduated cylinders. One obviously has liquid in it, the other does not. And I have two tubes that I'm going to use to transfer those liquids to illustrate how you can have a forward reaction as well as a reverse reaction taking place at the same time. Now at a certain point, after several transfers have taken place, we're going to notice that the levels of the liquids in each cylinder stop changing. This is a point that we call equilibrium, a point in which the transfer of liquid from one equals the transfer of liquid from the other. Here we go. Now, if you thought I meant that I was going to have equal levels of liquids, that's not what I said. I said that there'd be a point in which the levels stopped changing, and we've reached that level. In the original cylinder, I have just a little bit left, about 7 milliliters or so. Meanwhile, over here, I have roughly about 42. We lost a little bit in the transfer. That's okay. You may have noticed the last several transfers, nothing really changed. There comes a point in time in which this tube, even though it's very large, only has so much that it can transfer over. Meanwhile, this tube, even though it's very narrow, has a lot with which it can transfer, and so the end result is they're transferring the same amounts. We have the same forward rate as we do the same reverse rate. And this is the idea of equilibrium, that you can have a forward reaction and a reverse reaction, and at a certain point, you're going to see that those reactions begin to level off, that the rate of forward reaction is equal to the rate of the reverse reaction. Now it may look to us like a reaction goes from left to right, goes to completion, that's it, end of story. But that's not really the case because of equilibrium. You see, most reactions don't go to completion, they just are reversible. And they get to a point in which the forward reaction and reverse reaction have equal rates. Let's take this reaction for example. The reaction of nitrogen and hydrogen to form ammonia. There's also a reverse reaction there, ammonia breaking down to form hydrogen and nitrogen. So the way that we designate this is to rewrite the equation, but we use a double arrow to indicate that that reaction is indeed reversible. So there will come a point in this reversible reaction when the forward reaction of nitrogen and hydrogen becoming ammonia is equal to the reverse reaction of ammonia breaking down to form hydrogen and nitrogen. We call that chemical equilibrium, when the forward reaction rate is equal to the reverse reaction rate. Think back to the graduated cylinders and the tubes. Remember, even though one tube was bigger than the other, we still got to the point in which the transfer rates became equal, didn't they? That's like equilibrium. So you can have a forward reaction that could be stronger or a reverse reaction that could be stronger. But there's going to come a point in which the rates of both of those become equal and the transfer will be the same. Now we could also think of it like balance, except it's what we call a dynamic balance. Both sides constantly moving to keep the whole system in balance. That's what equilibrium is. There's still a process happening, it's just that the process forward is the same as the reverse. Complete balance. So in 1864, a couple of Norwegian scientists came up with this idea, the law of chemical equilibrium, which says that at a given temperature, a chemical system, a back and forth, might reach a point in which a particular ratio of products and reactant concentrations can have a constant value. As an example, we have a generic reaction here, a reversible reaction, A plus B yields C plus D. Okay? Now these little letters in purple represent any kind of coefficients that we might have in front of each of these. The K value the equilibrium constant value of this reaction would be the concentration of C to the little c power times the concentration of D to the little d power over the concentration of A to the little a power times the concentration of B to the little b power. Remember, products always over reactants, and only at a specified temperature. So let's do an example. So let's use our previous example equation. Nitrogen and hydrogen yields ammonia. It's a reversible reaction. We have the coefficients in place. I've put my expression for KEQ, and that is that KEQ, the equivalent constant for this reaction, is equal to the concentration of ammonia to the second power over my reactants, the concentration of N2 to the first power. See, no coefficient means there's a 1 there. I don't really have to put the 1 here, but for the sake of not causing any confusion, I put it there. Times the concentration of hydrogen to the third power. And that would be my expression for the equilibrium constant for this reaction. K can also tell us a lot more about the reaction than you might think. If K is equal to the concentration of products over reactants, then if K is greater than 1, it means that the end result is that we have more products than we do reactants, right? So therefore, in that reaction, the products are favored. But if K is less than 1, that means the reactants are greater than the products, aren't they? And so therefore, reactants are favored in that reaction. Something else to consider. In the case of this reaction we just did, notice that all three are gases. This is what we call a homogeneous equilibrium, where each compound in this reaction has the same state of matter. But what happens if we have a heterogeneous equilibrium? Here's an equation that will give us a heterogeneous equilibrium. Here we have sodium bicarbonate, solid, sodium carbonate, solid, carbon dioxide gas, and water vapor. I went ahead and wrote out my expression for KEQ here, putting my products on the top, the concentrations of each product on top, divided by the concentration of my reactant, in this case, to the second power, since there's a 2 in front of my sodium bicarbonate. Here's the thing. Any pure substance, solid or liquid, because their densities don't change at a particular temperature, that means the solid concentrations or liquid concentrations of pure substances will be seen as being constant. You're probably saying, all right, Mr. Risley, what are you saying? What I'm saying is we can simply cancel those out and not use them in our final KEQ because the concentrations of those things won't change no matter how much we put into it. Get it? So now our KEQ becomes this. Simply the concentration of CO2 multiplied by the concentration of H2O. Because a solid or liquid pure substance doesn't have a changing density, that means it doesn't have a changing concentration. So no matter how much we put in, the concentration will stay the same, which means that's a constant, and we can just disregard it for our final KEQ expression. Now, using these equilibrium concentrations for each of these compounds in this reaction, let's try to find out the actual value of KEQ for this reaction. You ready? Okay, first, I've written out my equilibrium constant expression. KEQ is equal to my product, HI to the second power, right, over the concentration of hydrogen to the first power times the concentration of iodine to the first power. All of these are gases, so all of them will count towards our final KEQ value. So now all we have to do is fill in the numbers. So now I've done that. 1.8682 to the second power over 0.06587 and 1.0659. All that's left is the math. So my final KEQ value is 49.71. One thing to note, Even though these values are in molarity, we don't have to put any values for our KEQ. It can just be a number. It can be dimensionless. Hey, while I'm thinking of it, what does this mean in regard to this reaction? Is it product favored or reactant favored? Product favored. Since KEQ is greater than 1, it means we're going to have more products than reactants. A pretty good bit more, as it turns out. All right, here's your problem. Here's the reaction of phosphorus pentachloride that yields phosphorus trichloride and chlorine gas. At equilibrium, their concentrations are 0.135, 0.550, and 0.550. What I want you to do for me is to find the value of KEQ, not just the expression, but the value of KEQ. And tell me if this reaction is reactant favored or product favored. So that's all for today. What have we learned? Well, quite a bit actually. We started out by talking about reversible reactions, how you can have a forward reaction and a reverse reaction at the same time. And that led us into the idea of chemical equilibrium, this dynamic, constant back and forth between forward and reverse reactions. That led us to the law of chemical equilibrium, where we said at a given temperature, a chemical system can reach a point in which a particular ratio of products over reactants can yield a constant value. We even gave an example of how you can put together a KEQ expression based on a particular reaction. We also talked about homogeneous equilibrium and heterogeneous equilibrium, and how in heterogeneous equilibrium, if you have a solid or liquid that's a pure substance, you can disregard it. It doesn't factor into the final KEQ expression. And lastly, we showed how you can actually solve for the value of KEQ if you have the concentrations of each compound at equilibrium. Wow, what a day. I hope you learned a lot, and I hope it was a good day for you. If I can answer any questions for you, please don't hesitate to email me. Can't wait to see you guys, but until next time, God bless.